So maybe I can spend some time to talk about the project. So I hope all of you have already met with your team member, either face-to-face or on Zoom. So this time, I think there are more team members in each team. So I think you can get more help or to double check your answers. So right now we haven't talked about the lime injection or chona injection yet, but we're going to talk about them this week. So I'll also demonstrate some calculations on what are the design parameters. Although it's not exactly the injection problem, but it's going to be a similar method because we're going to spend time talking about the lime or chona scrubbing. And dry injection is quite similar to the scrubbing process. But other than that, I think in terms of the design for the pre-cleaner or the ESP or the backhouse, you guys should have a clear idea on how to do that already. So one thing I do want to point out is that the pre-cleaner mentioned in the project, that is the cyclone. Okay? So it's not something else. So the reason why we also call that as pre-cleaner is we don't want to introduce all the particles into the ESP or backhouse. So, and we mentioned that cyclones are low cost, right? And it also can remove a lot of larger particles. So in that way, we can we can kind of pre-clean the flue gas and then send it to the control devices. So let me see. So when you design the cyclone, you need to use a size distribution of the particles or of the fly ash. So you can either refer to published articles, or if you want, you can also use the examples on our textbook. But also you need to make sure that those size distributions are actually for the fly ash, not for something else, right? So if you refer to those size distributions, you should also list the publication, right, the reference, so that others can know type of size distributions you're referring to. I think you can also find more information about the coal composition from the fact sheet that I uploaded on Canvas. So try to use that to assume certain chemical composition for your coal that you assumed in this system, okay? Yeah, so finally, one thing is that for this coal-fired power plant, I didn't give you a efficiency, like the operating efficiency. And you can notice that it's called the supercritical coal-fired power plant. So you can actually find more information about this type of coal-fired power plant. Generally, their efficiency is higher compared to the regular coal-fired power plants. Okay, so I can just think of these points for now. So if you have any questions, I think now is also a good time that you start to email me, schedule a time for the office hour, so we can discuss this project either with the entire team or just on like a personal basis, right? So I think we can get started on our class. So we need to continue our discussion on the sulfur dioxide removal. Right. So I think we introduced this concept last Monday. It has been quite some time, so we can spend more time doing the recap, right? So first I want to talk about the midterm scores. So the average score is around 40 out of 50. I think it's not bad. It's actually a little bit lower compared to last year. I think mainly maybe it's because of the remote learning, and also compared to last year, I also add one more problem to the exam. So the additional problem was the size distribution, the one that you use the dotted lines to calculate what is a DPG, what is a sigma G. I thought that should be a quite straightforward problem, but maybe that's occupying more time in your exam. So I think that's still not bad. It's pretty good. Okay. So the highest score in our class is the full score, 50, and there are 5 of you guys who get full score. So I think that's also a pretty difficult job to do. So congratulations to them. So I found that the common problems made in this exam is mainly about the last two problems. So the first one is about the ESP design. And the major problem for this one is that a few of you use the method in the textbook, right? So for the textbook method, it's basically using n minus ns, right? And then equal to some value there. And then let's say A, okay? So ns is the number of the mechanical fields. So if you use this method to calculate the total number of plates, you can find that n is somewhere around 77.3, maybe 77.3. So basically, you can directly round it up to 78, right? We mentioned that we have to round up to guarantee the efficiency. But also we need to make sure that this total number of plates have to be divisible by the number of mechanical fields, okay? So it has to be divisible by 4. So that's why you further need to round it up to 80. So that is the final answer for this total number of plates we need here. But if you use our method that we went through during the class, basically that's, I think that's n minus 1 multiplied by m, okay? So in this way, we automatically assume that the total number of plates, which is m multiplied by n, that's going to be divisible by the number of mechanical fields. So in this way, you can directly get the answer equal to 80. All right. So that is a problem for the ESP design. So for the backhouse design, I think the general problem is that some of you guys forgot to convert the unit to the square foot. Okay, so you can first calculate what is the total area in square meters, and then you need to convert it to square foot. And then you can find out that the number of compartments we need are going to be 6 to 7, not 2. Okay. So once you get this value here, you can further design the detailed structure of each compartment. I think all of you guys were quite clear on this aspect. So I mean, it's quite I think mainly because most of the problems are due to these two. And then generally we'll deduct around 10 points for these two problems added together. So that's probably why the average score is around 40. Okay. So if you have additional questions on the exam, feel free to email me. We can schedule an office hour to go through the questions there. Right. So now let's go back to the new materials. So we're going to pick up about the sulfur dioxide control. Okay. So basically last week we mentioned that we're very interested in sulfur dioxide, mainly because it's a criteria air pollutant, right? And then we also mentioned that there are two methods where we can remove the sulfur dioxide or remove the sulfur. So one is called the fuel desulfurization. So fuel desulfurization just means that we're going to remove the sulfur that's existing in the fuel. So we mentioned that the industry that's used this fuel desulfurization the most is the oil refinery. So they generally use this method mainly because they don't want to distribute this, for example, to the customers while these gasoline contain a lot of sulfur, because we know that sulfur dioxide is bad for human health, right? So let's say if we go to the gas station and get some gasoline there, and then we decided to turn our car in our garage. So if they did not treat any sulfur in the gasoline, then it's very highly toxic, right? So the customer might directly sue the gasoline company. So that's why the oil refinery will tend to deal with this problem before they distribute the product, right? So that's typically conducted in the oil refinery. So we mentioned that the way we do it is to add hydrogen to the crude oil, right? And then basically extract this sulfur out. And we get hydrogen sulfide, okay? So, in this way, H2S. Okay, so we can extract the sulfur from the oil and then get the hydrogen sulfide. And we mentioned that before the year 1970s, what the oil refinery does is they will just combust this hydrogen sulfide, right? And then they directly get water and sulfur dioxide. So instead of sending the sulfur dioxide to the customers, the oil refinery will just combust the hydrogen sulfide and emit sulfur dioxide at their plant. Okay, so we mentioned that this is not a solution to the pollution; it's just a redistribution of the pollution, right? And we mentioned that after the year 1970s, because of the EPA, we put more regulations to the sulfur dioxide emission. So environmental engineers got imaginative, right? So we can think of a way to deal with the problem of both the hydrogen sulfide and the sulfur dioxide. So this process is called the Claus process, and it's using this chemical reaction to deal with the problem. So basically, you can use two numbers of the hydrogen sulfide to react with the sulfur dioxide. You get three numbers of sulfur and two numbers of water. Okay, so we mentioned that this is a typical two-bird, one-stone problem, right? So we solved the problem of both the hydrogen sulfide and the sulfur dioxide, and we're generating a very expensive or very valuable product, which is a solid sulfur. We mentioned that this solid sulfur actually supplies more than 90% of the sulfur in the United States. Okay. So this is how we deal with the sulfur in the fuel. So we also mentioned that for the coal-fired power plant, let's say we mentioned that in terms of the source of the sulfur dioxide emission, basically 2/3 of them are coming from the coal-fired power plant. And then 1/3 is coming from the oil refinery. Okay, so in terms of the coal-fired power plant, we also did a simple discussion on why we couldn't use this fuel desulfurization to deal with the sulfur problem. So here I will launch a poll and ask you a question. So why can't we use this Claus process for coal desulfurization? Okay, 5 more seconds. Okay, we'll stop here. So the correct answer should be the second one. And this is mainly because the coal is a solid. So just consider what is happening in the oil refinery, right? So we're dealing with liquid oil. So if it's a liquid or in the gas form, we can easily heat it up to get the gaseous species, right? So if it's either in gas form or in liquid form, we can easily extract the sulfur out of the reactants. But if it's a solid, then if we simply draw a structure of a coal, right? And then although we can react the sulfur that's at the surface of the coal particles, it is very difficult to reach to the center of the coal, right? And because of that, it's going to be very slow in terms of the fuel desulfurization for the coal particles. And if you have already gone through the chemical compositions of the Eastern Kentucky coal in your team project, you can find that the sulfur content can be as high as 5%, right? 5% is very high. So the third option is not correct. All right. So because of that, we have to deal with the sulfur after the combustion. And that is why we need to use a process that's called the flue gas desulfurization. Okay. So the flue gas is basically the product coming out of the coal combustion, right? It's going to contain carbon dioxide, water vapor, right? And always when we combust coal, we'll feed in extra air, right? Because we want to completely use the energy out of the coal particles. So in the flue gas, we're also going to have oxygen and nitrogen. And of course, we have to have nitrogen there because nitrogen doesn't react during this process here. Okay. And then because of the sulfur in the coal, we're going to have sulfur dioxide. Okay. So there are many other types of gaseous species in the flue gas. And in your project, you're also going to go through those chemical compositions. So we have to deal with the sulfur dioxide that's in the already combusted air, okay? And generally, we will use a setup that's called the scrubbing or the scrubber to remove the sulfur dioxide. So when we talk about the PM control, we mentioned that there's also a system called the particle scrubber. So if you remember, there's a device that's similar to the cyclone where the particles move inside, but you also have a nozzle to spray water outside, right? So basically the water droplet can get in contact with the PM, make it larger, right? If it's larger, then they're going to have a higher inertia and then get easily captured. So the scrubber for the sulfur dioxide are going to be a little bit different in terms of the detailed design, but it's also using water droplet to deal with the problem, okay? And by the way, scrub just means wash, right? It means cleaning. So the scrubber means that we want to clean the sulfur dioxide out of the flue gas, okay? So there are many ways for the flue gas desulfurization or the FGD. For example, we have the limestone scrubbing. So the limestone scrubbing is the most widely used method for the sulfur dioxide control. Okay, it has been there for quite many years, and many coal-fired power plants in the world are actually using the limestone scrubbing, mainly because the limestone is very cheap, right? You can just dig some rocks and then grind them into tiny powders and then use them to deal with the sulfur dioxide. And then, so there's also a system called the lime scrubbing. So instead of using the limestone, we change the chemicals or change the reactants to lime, which is mainly composed of the calcium oxide, right? And then we can also use the lime spray drying. So this is more dependent on how we introduce these reactants into the system. And then we can also have the trona injection or the lime injection. So this is a relatively new technique for the sulfur dioxide control. And it's also dependent on where we inject these reactants into the system, okay? So here I'm showing a schematic diagram of the limestone scrubbing system. So what happens is we're going to introduce a flue gas from the bottom of this scrubber. Okay, the flue gas can contain, as we mentioned, nitrogen, carbon dioxide, sulfur dioxide. We may also have some nitrogen oxides in there. It really depends on whether we remove these nitrogen oxides beforehand. Okay, so the flue gas are going to be introduced here, and this is the outlet. Okay, so as you can imagine, the air will just go upwards, right? And then at the bottom of this container or this reactor here, we have water, and then we also will basically we'll also introduce the grinded limestone or the limestone slurry. So what we can do is we can mix them together, and then feed them into the spray tower. So the spray tower is going to generate tiny droplets that's containing the calcium carbonate, which is the limestone, and then they're going to fall down, right, because of the gravity. So we have the flue gas that's going upwards, and we have the droplets that's going downwards, right? So there's going to be a more better contact in terms of the flow and the liquid, right? So we mentioned that there are sulfur dioxide in the flue gas. Sulfur dioxide is an acidic gas, right? So it's going to react with the component that's in the limestone, which is the calcium carbonate. So the reaction that's taking place going to be sulfur dioxide react with the calcium carbonate. And we're going to have the calcium sulfite. And carbon dioxide. Okay, so basically we're replacing this cation here. Okay, so we're going to have calcium sulfide and carbon dioxide. Okay, so everything is happening basically at the surface of the liquid. Okay, so we have the gas molecules, right? The gas molecules are going upwards, and we have the droplet going downwards, right? And then the sulfur dioxide will just react on the surface of the liquid, and then we can get this calcium sulfide here. So the calcium sulfide actually has a relatively low solubility, okay? So in this spray tower here, so once the reaction takes place, finally these water droplets are going to fall down to this reservoir here, right? So this is going to be a solution containing water and also the calcium sulfide, okay? So we also mentioned that the calcium sulfide has a low solubility. So they're going to settle down, right? And then basically at the bottom of this reservoir, we can form solid particles or basically solids containing these sulfide here. But one thing we also know is that the calcium sulfide or these sulfide ions are not stable. So they can easily get oxidized by oxygen, right? So what happens is calcium sulfide can react with oxygen to form calcium sulfate. So the solubility for the calcium sulfate is further lower. Okay. So what this means is that we can further introduce oxygen to this reservoir here, right? And then let the calcium sulfide to react to form calcium sulfate, which means that they are going to be more stable. And also, due to the further lower solubility, we can form more solids, right? So we can form the calcium sulfate here. And then finally, at the bottom, we can just extract the solid out. And then further, we can dry them out, right? And we can form this solid called the gypsum. So gypsum is mainly composed of the calcium sulfate. So basically, in this way, we extract the sulfur from the flue gas to fix them into the solid, okay? So the reason why we want to form gypsum is also because it's a raw material for construction, okay? So in the civil engineering, you typically use these gypsum to as an ingredient for the constructions, okay? So basically from this process, not only we remove the sulfur dioxide from the flue gas, we also form some valuable products out of it, right? So this is a limestone scrubbing. And here I have a short video about the mechanism. Let's see. Let me just open this up.
In some instances, sulfur dioxide from combustion is removed from the flue gases by using it either to produce sulfuric acid or gypsum for construction. These products can then be sold to help offset the cost of running the flue gas desulfurization plant. In both cases, oxygen is used to help encourage the necessary reactions that need to take place.
So by the way, if you further look at this system, you see, what is this? So this is the ESP, right? We have a lot of plates inside to remove the particles. And then after the flue gas is cleaned of particles, we introduce them into this limestone scrubber or lime scrubber here. So there are going to be droplets falling down and the flue gas will go upwards.
In the case of sulfuric acid, adding excess air to the sulfur dioxide and vanadium oxide converts it to sulfur trioxide, SO3. When combined with water, this produces H2SO4, or sulfuric acid. In the case of gypsum, limestone slurry used in wet scrubbing processes combines with sulfur dioxide to produce calcium sulfite. When subjected to a forced oxidation process involving the addition of water and oxygen, the sulfite is converted into gypsum.
So this is what happens during the limestone scrubbing. So we'll first form the calcium sulfite, right? And then we'll add further air or oxygen at the bottom of the scrubber to form the calcium sulfate.
In addition to these processes, oxygen is also required in flue gas desulfurization processes using seawater. As the seawater absorbs the sulfur dioxide, oxygen is added, creating a mix of sulfate ions and hydrogen, which in turn converts to water and CO2 gas.
So this is the scenario where if the power plant can be built nearby the seashore, right? And then people can directly use the seawater to absorb or to remove the sulfur that's in the flue gas.
In all three cases, using an oxygen probe to accurately measure oxygen concentrations can help to regulate the conversion of sulfur dioxide.
Right. So you can see that oxygen is also quite important in terms of this conversion process. So in the share screen, I don't have a animation here, but here you can see better how does the system work, right? So we have the flue gas going upwards, and then we have this spray tower to spray down the droplets, and there's going to be a better contact between the gas and the liquid. And then at the bottom, we're going to introduce air or oxidizer into this mixture here or into this solution here. And finally, we can get the gypsum at the bottom. And basically, you can see here that we introduce the limestone and then combine it with water to form the slurry and then bring it up, right? So this is the limestone scrubbing. And we can also use the lime scrubbing. So lime scrubbing just means similar setup it's going to be used here. So instead of introducing the limestone, we're going to introduce lime here, right? So we know that once the lime react with combine with the water, it's going to form the calcium hydroxide. So calcium hydroxide is a strong base, right? It's going to react better with the sulfur dioxide. So basically the chemical reaction will be more complete. in this way. And that's lime spray drying. So what lime spray drying means is basically we're going to get rid of this reservoir here, okay? So what we can do is we can better control the size of these droplets. So for example, originally, let's say these droplets are 1 micrometer large, 1 millimeter large, okay? So if it's 1 millimeter large, then they're large enough that when they settle down to the bottom, they're still quite relatively large, although there's evaporation taking place, but they can still settle down to the bottom. So now let's say that instead of generating these larger droplets, let's change them to 10 micron droplets, okay? So they're going to be very small, right? And by making them smaller, the reaction will also be faster, mainly because we're exposing more area of the solution to the flue gas there. And then the other thing that's happening is once we spray these droplets down, while they're settling down, they're also evaporating, right? And then basically we can design this system that before they settle down onto the bottom, they're small enough that they can get carried by the flue gas and then further get exit from this scrubber here. So we're not forming any water solution anymore. So we're basically forming PM, right? So we introduce very small droplets, right? Again, we're introducing very small droplets here. While they evaporate and react, they become smaller. And once they become small enough, their gravity is not strong enough to let them settle down onto the ground. And then they're just going to go with the flue gas and then exit this spray tower, okay? So you can also see that once they exit there, we're going to form a lot of particles, mainly because of the reaction that's taking place, right? So by having this lime spray drying process, what that means is that after the spray tower, we need to further introduce that into a PM control device, right? For the lime spray drying. So for the limestone scrubbing or lime scrubbing, where we have this water reservoir here, we don't need to worry about the PM removal. So generally, we'll get rid of the PM in the flue gas, and then introduce the flue gas that's mainly composed of the sulfur dioxide into the scrubber. And then after it's being cleaned by the sulfur dioxide, we can directly emit into the atmosphere. But for the lime spray drying, since we're not collecting any solution, so all of these droplets are going to convert into tiny particles. What that means is that we cannot directly emit these flue gas into the atmosphere anymore. We have to clean the particles inside. And then for these systems, they generally just were set up upstream of the PM control devices, okay? And it is the same for the trona injection. So trona injection also doesn't need any water reservoir there, okay? You don't need to handle any liquid. So what that means is we can just directly introduce the solid into the combustible or combusted air, and then let the reaction to take place directly in the flue gas. And since we're directly introducing solids, right, we're not going to form any liquid. And then once we form additional PM, we can introduce them into a PM control device, okay? So here, basically, I'm listing out the method where basically that's the device that we're going to design in the team project, right? So for these trona injection or the dry adsorbent injection, what we're going to do is we're going to set up the injection point at here, okay? So this is the entire coal-fired power plant system. Basically, we will introduce the coal particles in here, form large flames, right? And then these are the combustible gas or the combusted gas. And then we'll go through these bends, right? The water boiler or the water pipes are going to mainly be here for the exchange of the heat. And those steam will further get transported somewhere else to generate the electricity. And then you can see that the flue gas will go through basically these devices. These are called the selective catalytic reduction. That's mainly for removing the sulfur oxides. And then after these devices, we're going to introduce the dry sorbent. So these can be lime or these can be trona. Okay. So for this process, it doesn't involve any liquid, right? It doesn't involve any slurry or forming the gypsum process. So we're just directly introducing these reactants into the flue gas and then let the sulfur dioxide to react with this solid here. Okay. So after this process, we can further introduce some activated carbon, but this is not required for your project. And then these additional PM. So as we mentioned, we're introducing these dry particles in the flue gas. We're generating more particles, right? So that's why we have to introduce them into the PM removal device, which is an electrostatic precipitator. And then theoretically, we can directly emit it into the atmosphere by sending it into the stack. But I think in this diagram here is adding one more wet scrubber to further remove the sulfur dioxide or remove other toxic species. And you don't have to include this part in your design there. So basically, for your design, you want to include the dry sorbent injection, where you inject either lime or trona to let them react with the sulfur dioxide. And then you need to design the PM removal device, which contains the pre-cleaner or the cyclones and the ESP. Okay. So this is basically a brief overview of what you're going to deal with in your design here. But one thing we haven't dealt with yet is how do we do the calculation, or how much, let's say, how much lime do we need, how much trona do we need in order to neutralize the sulfur dioxide, right? So let's just finish up with some chemical reactions in here. So if we introduce lime in the system, if we use the lime scrubbing, then we're going to form the calcium hydroxide. And then similarly for calcium hydroxide, it can react with the sulfur dioxide and then form calcium sulfide and water, right? And similarly, we can introduce oxygen at the bottom of the scrubber and to convert the calcium sulfide into calcium sulfate, right? And then for the lime spray drying, so since we're still going to use a spray, right? And then we should be able to form the calcium hydroxide, right? And then we're going to go through the similar reaction to form the calcium sulfite, water. And the water here just get evaporated, right? We mentioned that the spray drying doesn't need any liquid reservoir here. So what we do is mainly we reduce the size of these droplets so that they cannot settle down onto the ground and they're being carried away by the flue gas, right? And in terms of the trona injection or the lime injection, then it's directly these species reacting with the sulfur dioxide, right? And then we can form the sodium sulfite. And then sodium sulfite can further react with oxygen to form the sodium sulfate, right? And in terms of the lime injection, for the dry injection, then it's just going to be calcium oxide, react with the sulfur dioxide to form the calcium sulfide, right? So this is a reaction, or these are the reactions that we're going to use in terms of different sulfur dioxide removal systems. And from these reactions, we can also find out what is the stoichiometry we need, right? For example, if we use lime spray drying, then for each mole of the calcium hydroxide, then we can react with 1 mole of the calcium, 1 mole of the sulfur dioxide, right? So these are about the reactions that's taking place. And then we need to talk about how do we design the system, okay? So here I'm showing the limestone scrubber again, right? So basically what happens is we introduce a flue gas going upwards. We're spraying these slurry droplets going downwards. they're going to react, right? And finally, we get clean gases. That's basically the sulfur dioxide or nitrogen oxides are getting removed. And at the bottom, we can form the gypsum as a product. So let's say if we already know the amount of sulfur dioxide that needs to be controlled, right? This is generally the situation for coal-fired power plants. So let's say for the exam problem that you dealt with, in the exam, I think the second problem is giving you what is the capacity of the power plant, right? It's assuming 500 megawatts, and further it's assuming a certain content of the sulfur, right? It finally asks you how much sulfur dioxide it emits into the atmosphere per day, right? So for that problem, the final answer was 32 tons of the sulfur dioxide per day. So typically for a coal-fired power plant, we already know what is the total formed sulfur dioxide, right? And then the target or the purpose of these scrubber or these sulfur dioxide removal devices is just to neutralize the sulfur dioxide that's in the flue gas, okay? So let's say we consider a very simple scenario. For example, our coal-fired power plant generates 32 tons of sulfur dioxide per day. So how much of the calcium carbonate, how much of the limestone do we need per day? Okay, so this is just based on the stoichiometry, right? So we know that sulfur dioxide react with calcium carbonate to form calcium sulfide and carbon dioxide. So everything is 1-to-1 ratio. So each mole of the sulfur dioxide is going to react with 1 mole of the calcium carbonate, right? And then let's first consider, for example, we consider 32 grams of the sulfur dioxide. So how much of the calcium carbonate does it need to react with it? So we know that the molecular weight of sulfur dioxide is 64, right? So it's just 32 plus 2 multiplied 16, that's 64 grams per mole, right? If we have 32 grams of the sulfur dioxide, that means that's 0.5 mole of the sulfur dioxide. And due to the stoichiometry, it can react with 0.5 mole of the calcium carbonate, right? And for the calcium carbonate, so the molecular weight is 40 plus 12 plus 3 multiplied by 16. That's 100 exactly, okay? So what this means is that if we react with 0.5 moles of the calcium carbonate, so the weight of the calcium carbonate is going to be 50 grams. Okay, so for this problem, we need to control 32 tons of the sulfur dioxide per day. What that means is that we need to provide 50 tons of the calcium carbonate per day. Okay, so this is very simple stoichiometry, where we assume 1-to-1 reaction, 1-to-1 ratio of the reactants here, right? If we know how much sulfur dioxide we need to control, then we can calculate how much of the limestone we need to provide it to the system, okay? But in reality, there are a lot of things that will complicate this problem. So for example, should we use the exact amount that's required by the stoichiometry? Probably not, right? Because we know that the reaction is not taking place completely. For example, we're talking about the gaseous species reacting with the liquid here. So first, let's say if we draw out the liquid, then this is a gas of the sulfur dioxide. So the sulfur dioxide need to first get in contact with the calcium carbonate that's at the surface, or some of the sulfur dioxide need to dissolve or get absorbed into the system. Okay, so that's going to take time, right? And if we cannot control the time or the residence time of the droplets, if it's very short, then the sulfur dioxide cannot completely react in this system. So we always need to provide extra of the reactants to neutralize the sulfur dioxide, okay? So generally people will just provide 10% more of the limestone or lime into the system to let it better react with the sulfur dioxide in the system. Okay, and also one thing we need to make sure is that so here we were assuming that the limestone is composed of or completely composed of the calcium carbonate, but in reality the limestone is composed of many impurities there. For example, it can contain, of course, most of them is calcium carbonate. But there are also magnesium carbonate, and there are a lot of inert inside. Or let's say clay or some other species that just cannot react with the sulfur dioxide. Okay, so because of this reason, we need to provide more limestone into the system, right? Let's say if the limestone just contains 50% of the calcium carbonate in terms of mass, then we need to double the amount of the limestone we introduce to the system, right? Because there are not enough of the calcium carbonate to react. Okay, so now we can look at a actual system. Okay, so this is the example problem that's given on your textbook on page 506. And this problem basically wants you to design a sulfur dioxide scrubber system. Okay, so it's talking about a 500 megawatt power plant, and also provides you what is the sulfur content in their code. And then this is basically a table that's showing the flue gas composition or flue gas characteristics. Okay, so I would expect a similar table in your team project, mainly because they list all the components in the flue gas that you're going to deal with. It has, for example, particulate matter, carbon dioxide, hydrogen chloride, nitrogen, oxygen, sulfur dioxide, and moisture. This is just water. Okay, so you should also calculate what is the flow rate of these species per unit time, right? So this here is providing per hour. Okay, so I would recommend you to use standard units because it's easier for calculation. But here, your textbook is still using the pounds in terms of the flow rate there. But I would say that for your calculation, for example, for the supercritical coal-fired power plant, you should expect similar values compared to this problem. Okay, so for our problem, we're designing 300 megawatt. Okay, it's a little bit smaller, but the values are not different should not differ in orders of magnitude, right? So you can convert your calculation to these units here, and then see if you get similar values or similar order of magnitude. So if they're in the similar order of magnitude, then it means that your calculation should be correct. If let's say if it differ by 2 orders of magnitude, then it's likely that there are some problems in there. Okay, so I would expect that you also generate this table here because it's going to be more straightforward for your calculation in terms of other devices. Okay, so you can see that generally in the flue gas, there are many species in there, but we're trying to deal with the hydrogen chloride and the sulfur dioxide. Okay, so not only sulfur dioxide, there are also other acidic gas species which can react with the limestone or lime. So we assume that there are 90% removal efficiency of the sulfur dioxide and complete removal of the hydrogen chloride. And we need to calculate what is the feed rate of the limestone per hour. Okay, so this is going to be a similar question for your project. We assume certain removal efficiency of these acidic species. We need to calculate how much of the lime or trona we need to inject into the system. And further, we need to calculate what is the production rate of the sludge. So basically the sludge is everything that's collected at the bottom of this reactor here, right? Because we also need to deal with the products from this reaction. So we further, by assuming there are certain compositions in terms of the sludge, let's say 60% is water, 40% is solid, we need to calculate what is the production rate here. And here are also some assumptions that are being made for this realistic problem. I think due to the time constraint, we should look at this problem next class. so we can go through a more detailed calculation in terms of how do we analyze this problem. Okay, so if you have time, I would recommend you to go through this problem beforehand, before our next class. You can get a better understanding here. Okay, so that's all for this class. Let me know if you have any questions.